office hours, whenever you want. Let's see. So today we're going to start talking about interpolation and curve fitting. This is going to be another kind of funny one. Interpolation is pretty straightforward. Curve fitting technically brings us into optimization, which doesn't actually get covered until 2 weeks from now. So this is one of those things that like we're going to start off on one side, but we need to get that side because a lot of the optimization routines use interpolation algorithms, but we need the optimization in order to get to the curve fitting one. And it's just kind of, it's ultimately this sort of thing is like a non-linear path, and we're just going to have to do the best that we can to go sequentially through it, because otherwise it gets too mixed up in our heads and things. So bear with me through that one. It just means that we're going to jump ahead and back and forth a little bit with optimization, but that won't be until Thursday. We'll get into the optimization part. We're going to cover one thing that I'm actually just going to skip over entirely to try and make space to do neural nets under the curve fitting, because everybody is hot to trot about neural nets and everything like that. So I thought it'd be interesting to kind of put it in here and teach you guys a little bit about like how that sort of thing works. Okay. So differences between interpolation and curve fitting. Interpolation seeks a curve that goes through all the points in a plot, right? That's kind of what you're doing when you're like fitting a curve, right? Just going like that. I shouldn't say that. When you're connecting the dots, even before fitting a curve. Anybody ever play connect the dots, right? Like what you're doing is kind of interpolating. It is assuming that there is no experimental error or measurement error in the data points that you're interpolating between. It's just kind of a foregone conclusion that these are absolutely right. There is no ambiguity in mapping between the X and the Y. I found it helps me a lot to conceptualize this thing. I don't think about a function anymore as taking an X and giving me a Y. My modern way that I think about it now is more kind of making that X and Y pair consistent. And that to me kind of makes a bit more sense and works a bit cleaner with some of these concepts. But however you choose to do that, just remember that whatever can be done can be undone. In general, with interpolation, there's no ambiguity. In that there are no duplicate Y's for a given X, right? So this goes back to the definition of what a function is. You can't have one X and have measurement of 10 and 11. Right? Because that would imply that there's some kind of experimental error, or you're not actually a function. You're not actually one-to-one. So we're excluding that. Interpolation, one-to-one. It is often used to capture the local behavior of things. As soon as you start to get into the global one, do you guys know what I mean by like local versus global? Yeah. Well, there's a good example in the class, actually, right? Your sense of hearing is generally local. Right? Like you can hear the people beside you, but you can't really easily hear the people on the other side of the room, right? And that kind of generality and that scope of perception makes certain algorithms work better for certain things and vice versa. It's also related to sparsity, actually, to matrix sparsity. Okay. In contrast, curve fitting seeks a curve that's a best fit for the data points. Who knows what best fit is? Good. There isn't a great definition for what best fit is. Typically, what they're talking about is the root mean error, right? So you take the not root mean error. Thank you. Right? R being the residual, being the difference between your prediction and your actual value. You square that, you sum that, that becomes your error. But even that, right? That will give you for a set of data points, the R squared will give you the difference between those, but you still have a vector. How do you assign a scalar value to a vector, to the magnitude of a vector? Somebody jump in. Right, you already answered one. Anybody? If I have a vector of values and I want to find the size of that vector, the magnitude of that vector. Gonna go back here. Yeah. The norm, right? Which norm? There's the Euclidean norm, which is the vanilla one. There's the infinite norm, right? Which is basically the max value. And there are a bunch of different ones, right? So there is no universally accepted in general case for the best fit. Generally, what people mean is the sum of R squared. Okay. Curves do not necessarily traverse all the data points, right? So if you have, let's see if I brought my whiteboard marker today. Yes. Point, 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 right? A line is technically a curve. This does not go through any of my data points, but it is probably roughly the best fit in some sense. It is a more global encapsulation of the data. I'm going to reword that line a little bit. It is a more global encapsulation of what the data is trying to say, I would say, right? Because if you have a bunch of data points and you're going like this, but they're all over the place because of all your error, right? This is not real, right? Your experiment doesn't actually do this. It's actually doing this, and you have everything else in the universe working against you that's giving all this uncertainty and noise in there. Okay? I'm also going to add there, it's generally simpler than interpolation, right? With what we're going to talk about next is that with interpolation, you can always find, like if I have n data points, I can always find a 10th order polynomial that fits those exactly. 10th order polynomial is big and nasty. You don't want a 10th order polynomial. You want a first order polynomial, otherwise known as a line, right? So curve fits are another way to get it to be a nicer form. And nice means computational profit when you actually go and evaluate something like this. Okay, so today we're going to go into interpolation. Tomorrow will be, not tomorrow. Oh, coffee. Thursday will be curve fit, and probably Friday rounding off with the neural network stuff. Actually, as it happens, this week is the Beyond the Prompt AI event. I'm pretty sure there's one where a couple of people are going to be teaching you how to build your own large language model. Not so large. Language model, LM. So if you are keen on this sort of stuff and you want to see like how ChatGPT and Gemini and stuff like that, I'm pretty sure it's John Fink that's giving that one. But I think it's either today or tomorrow. So if you're keen on it, let me know and I'll send you the link to it. Okay, we're not going to be going in that far. I'm just going to show you guys the basics. All right. Interpolation is a more fundamental concept because it's historically easier to do. We're going to know, have you guys ever heard of the difference engine? Historical machine? No, difference engine was I think it's the Babbage difference engine. It is the first computer, right? And today we're going to see what that computer actually did. Interpolation is both easier to do in the sense of calculating a value and expanding your data, your interpolation to include new data, right? So one of the first out applications of these computers were to take a bunch of data, you fit some kind of curve to it, but then you get new data point and you need to refit it, right? And this is back in the day when like fitting a curve was a monumental achievement requiring 3 technicians and like $1 million of funding, right? Maybe not $1 million, $100. In today's dollars, $1 million. Back then it was like $1. There are a few things to consider with interpolation. One is the speed of building the model, right? The speed of adding new data to the model, speed of executing the model for interpolated values, and then the generalizability. Right. What we're going to talk about today rely on the fundamental property of linear systems. It's always possible to construct an an nth degree polynomial that passes through n plus 1 data points, right? So a first degree polynomial is a line. A line passes through 2 data points, right? If you have 10 data points, then you need at most x9, right? Constant x9 plus something else, x8, blah, 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 blah. Generally speaking, that's a terrible idea. You're going to see why. We're going to be using this example over and over again. It's just a Gaussian curve. I'm just showing you to show you what it means to sample data, right? So you've got your nice curve. That's your real one. You take all these data points. And now the idea is if we didn't know what the true curve was, the blue one here, if we just had the red data points, how could we recover the original curve? That's what we're going to look at. Notice that these data points are evenly spaced. Okay, that's going to be a big differentiating factor between some of these algorithms. It's going to break if they're not equally spaced. So just take note of that at this point, that these guys are even. Moreover, I would say moving forward in your career, when you've got your algorithms and your computers and COMSOL and whatnot to do the curve fitting forward, learn to think about like evenly and non-evenly spaced. It makes a big difference for the numerics. So just take recognition of that. Okay, polynomial interpolation. It is a very straightforward approach to interpolation. We're going to talk about three methods of constructing the polynomial. Three different ways that we're going to construct this polynomial. But because for n+1 data points, there is only an order n polynomial that fits all of them, right? Then all three of these methods necessarily can only ever result in the exact same polynomial. So if we have 5 data points, there is a quartic polynomial, right? Something x4 plus something x3, x2, x1, right? We're going to talk about 3 different ways to figure out what those constants are, but they are all going to result in the exact same form. There is no ambiguity. It is 1-to-1. And you're going to see why, actually, at the end of this. You'll be able to show us why. Okay, Legendre polynomial interpolation. This is one of those things that I think they are actually implemented in NumPy and SciPy, Legendre polynomials. Legendre polynomial interpolation. It's not so widely used in for actual fitting of data. Actually, interpolation isn't so widely used, to be entirely honest. But it turns out that this guy is going to be very fundamental to a lot of the other algorithms. So the same way that Gaussian elimination, nobody actually does that in practice anymore. It still underpins a bunch of these things. The same way the Lagrange polynomials are going to be used again and again and again. Sorry, I didn't sleep very well last night, so I'm waiting for this coffee to kick in. This is actually the protein latte, and it's not bad. Apparently, it's like super hard to get a hold of because all the Timmies are just selling out of it. But if you like lattes, it's not bad. Okay. Legendre polynomial interpolation constructs the polynomial as, the algebra here is a little bit tricky, okay? What we're going to do is we're going to say that your overall function y is going to be the sum of, the weighted sum of your data points that you're given, your yi, and this p function. Pi is also indexed and is equal to this nasty expression here, right? And in 2 lines, we're combining sums, right? The sum, the addition between everything. And this is, do you guys know this, the symbol, product of? Same way a sum is the addition, like the series addition, this is the series product. So we just multiply everything together. Okay, and it goes like this. Let's give a little bit of, so let's actually blow this thing out and we can see what's going on here. By construction, and we're going to see why, when pi, so pi at xj, right? So the polynomial, the ith polynomial, let's say the second polynomial, at the second data point is equal to 1. And that polynomial at all of the other data points where the measurements, the x's, are going to be equal to 0. I'll show you. I'll show you an example and hopefully that'll be clear. This is a very nice property because it makes all the algebras simplify tremendously. Okay? So when I and j are equal to each other, then it's 1. When they're not equal to each other, then they're 0. So by way of example, let's get some data. 3 data points, 0, 0.5, and 2, right? And we've got the y values 1, 3, 2. So that, what would that look like? We've got the data point here, This is x0. No, I called that x1. I did my numbering bad, right? This is 0.5. That's x2. This is, sorry. This is 2, and this is x3, right? And then for the y values, we've got, what is this? 1, 3, 2. Okay, so we're looking for something that looks like that. What kind of curve is that? 3 data points. What kind of polynomial are we looking for? Second order parabolic quadratic polynomial. When you apply these things, so for each data point, and by data point, I mean x and y pair. So we've got 0, 1, right? We've got 0.5 and 3, and we've got 2 and what was the other one? 2? What we said? Yeah, 2 and 2. Okay. For each one of these data pairs, x, y, related by this function, we're going to write out one of these polynomials, one of these Legendre polynomials. The way we construct it is using this formula. And if you rattle through it, what you're going to get is x minus everything that is not I. So on the top, you're going to get x minus x2, right? So if the first one is going to be x minus x2 times x minus x3, right? We're skipping the x minus x1 part. And then on the bottom, we just have this permutation. So we get x1 minus x2, x1 minus x3. Does that make sense how that's constructed? Right? It's one of these, like, it's kind of a wonky format to construct this thing. You put it into your algorithm, it evaluates without a problem because that's what computers do. So right off the bat, if x was equal to x1, right? Then you would have x1 minus x2 cancels with x1 minus x2. And you have x1 minus x3 cancels with x1 minus x3. And this polynomial evaluates to 1. For all the other ones, if x is equal to x2, 0, everything's dead. For x is equal to x3, 0, everything is dead. Right? This is by construction that these polynomials are only equal to 1 for the associated data point, and they're 0 everywhere else. Once you actually put in the numbers, you plug that through and multiply, and you get this seemingly innocent parabola here. This is only the first Lagrange polynomial. You need the other ones too. You need the other ones associated with the other data points. So you repeat that, the exact same properties. Now you get this guy and this guy. And if we plot them, here's the code to plot it all. These are our polynomials. Okay, so for x1 here, blue at 0, which was our data point, the first one, this is equal to 1. 0 over here, 0 over here. The orange guy is associated with the second plot, 0, 1, 0. This guy, the green, is associated with the third, 0, 0, 1. So far, so good? Excellent. Then you assemble it. And then the question is, well, wait a second. What weights, right? The total polynomial, the total fit, is the weighted sum of these individual Legendre polynomials. I'm always missing Lagrange with Legendre. Lagrange polynomials. Sorry, not Legendre. Lagrange polynomials. It turns out, because of this property, that P1 is only 1 at x1, right? At this data point, we want the total function to fit some kind of curve, to fit our associated y value. Turns out to be 1. That's okay, right? This one would be 3, for example. Because this polynomial is the only one that survives at this data point, and it's exactly equal to 1. When you do the sum, what you're going to get is y at x1 is equal to something times P1 at x1 plus something at P2 of x1 plus something at P3 of x1. P2 at x1 is 0. P3 at x1 is 0. P1 at x1 is 1. So this guy is equal to our first data point, and that's equal to our something, right? So this whole, the nice thing about this is that calculation of those weights is super trivial. They are verbatim just your y values, your measured y values, once you've constructed these polynomials. And sure enough, this is the polynomial that we get when we apply that. So far, so good? Okay. Boy. So for n data points, we necessarily produce a unique polynomial that crosses each one. We cannot have two measurements at the same x coordinate. If you do, then that property that P1 is going to be 0 in some cases and 1 in the other cases, right, is going to break down. You're going to have 0, 1 over 0. Undefined, everything dies. Unless it turns out to be the exact same data point. That's the only case where it could work. That case is just degenerate. You may as well just knock it off. It's not helpful. Each evaluation of these p variables, or these p functions, involves So every time, so we've computed it all, and now we're just evaluating it. It's going to be n products here, right? So this is, okay, well, n minus 1, right? So we have 3 terms. So that's our input space, right? And this is 2 products. And it's just going to increase linear with that. But then there are n of these polynomials associated with that too. N by n means the computational complexity for this is n squared. Right? And that's just for the evaluation. Never mind the building of that. If we add new data, as written like this, what we have to do is restart the entire thing over. So Legendre polynomials, super popular. They result in a nice closed form, simple to calculate, especially for low level ones, but they don't expand very well. And n squared isn't actually great evaluation. Okay. What's the other thing here? If you use SymPy, you can see what the resulting expression is. So when we calculated all of these p values, these functions, then we have to do the weighted sum, right? The weighted sum of these guys are going to still include this unknown quantity x, which means if you just slap all these guys together, you're going to get a big, ugly, nasty polynomial that looks like this. Because you've got your weights, you've got x in here, right? You've got another one here. You've got to multiply through, distribute everything. You could simplify and get down to here, but now you're doing something else too. You built an expression, but it's not in its simplest form. And the reason why you would want that is because you're doing more calculations than you need to. A little bit of algebra, you could alleviate a lot of the complexity of evaluating these things. Computers aren't great for algebra, right? This gets into compiler optimization. To simplify this to something more useful, or you have to use a symbolic logic engine to do the same. Either way, it's nasty. Doesn't result in very clean form. Yeah, it can be shown that the error in the interpolation, right? So the y true for here, for example, right? That is not measured. We only have 3 data points. We want to evaluate it somewhere in between. What it can be shown analytically, we're not going to cover the proof, right, is that this is roughly equivalent to this. Again, you've got the product divided by this factorial times this function. And this function is actually uncalculatable. It's one of these like mathematical proofs that this value is somewhere in between the interval of x naught and here. Reason why I'm saying that is because what it means is that the further the data point is from X, the more it contributes to the error. So let's look at this for a second. The dominant, so look over here, right? This belongs to the function. Don't worry about that one. Just take a look at this product. If one of these guys is large, it's going to dominate everything else, right? Because this is the difference. So if X was close to, well, let's do this way. Say we want a value here. Okay? This is, what is that? 0.4. Okay? X1 is 0. So 0.4 minus 0 is 0.4. Okay? 0.4 minus X1, or sorry, X2 here is 0.1. 0.4 minus 2 is large, is 1.6. What that means is that when you crunch through the numbers, any uncertainty in this evaluation here is going to be dominated by the data point farthest away, which is kind of a bad thing. Generally speaking, we want our interpolation, our curve fit, our interpolation to be most affected by the data points nearby. We have this concept of locality. This guy should be mostly determined by these guys, but it's not. It's actually mostly determined, the uncertainty is mostly determined by this guy over here. Does that make sense in some way, shape, or form? Going to become a bit more clear when we talk about radial basis functions. Yeah. And even worse, there is how many polynomials to fit these data points? 1. So we're going to cover 2 more ways that we can calculate that polynomial. Guess what the error properties of those other 2 ways are going to be? Right? This proof, this error form here, is for the case of Lagrange polynomials, right? We're going to talk about different ways to construct that polynomial. And guess what those error properties are also going to be? Going to be exactly the same. Yes, yeah. They have to be the same because there is only one polynomial. So this isn't a problem with Lagrange polynomial interpolation. This is a problem with polynomial interpolation, period, which is much worse. Which is why people do splines. Spoiler alert. Okay, I'm already behind, so I'm going to go through this part really quickly. There are different ways that you can get to an analytically easier form to evaluate. Remember, back in the day, these things were programmed on punch cards when memory was like a vacuum tube, right? So any computational savings that you could put into this point, at this point in the game, was big, big payoff. Nowadays, who cares? We have computers that can fly us to the moon and back, right? If you try and improve the performance of the Lagrange interpolation, what you have to do is you have to simplify your analytic form. The way you do that is you define this new function, which is your sum of, or your product of all of these terms, right? All of them, not excluding the one that you're at. And then you define your barycentric weight to be this guy. You've got 1 over this function, and this is the everything but. Your polynomials now turn into this omega over this, much simpler, right? Before, this was all the product of. This guy removes that product operation, pre-computes it, and then it applies to every case. So you're not just recalculating the same thing over and over and over again. So this guy becomes your expression for your Lagrange polynomials. And when you do the sum, it factors out. So you take all this product nonsense, you compute it once, and then you just multiply that through again and again and again. What we've basically done, you know how I said that like this results in a whole bunch of polynomials that then need to be simplified? We have pre-simplified. That's what this is. It's taking your common terms, it's pulling them out so that you only have to evaluate them once. Why would you do that? It's because once you've computed everything, all you have to do is order n to evaluate it. So instead of n squared, from that simplification, from just reorganizing these terms, we've already gained one order of n here. Let's see. Calculation of these weights can be done recursively so that each one takes order n, in which case it takes order n squared to update. If you have another n on top of that, it only takes that. Note that these weights only depend on your x values, not your y values. Your y values only come in right at the end when you're doing this polynomial, when you're constructing this thing. And what that means is when you have, for these data points, if you know that your measurements are 0.5 and 2, you pre-compute everything, right? And then if you do the experiment again, and now you get data that looks like this, right? With that curve that you wouldn't know otherwise, you don't have to recalculate all your bases. The other nice thing is that you separate all the calculation associated with your x spacing, and then just leave the insertion of your y data points afterwards. Does that make sense? Again, back in the day when all this stuff was like punch cards and mainframes and ticker tape reading, my prof. So my thesis advisor had a dream of his future office. He was one of the original programmers of Gibbs energy minimization things for like chemical equilibrium and stuff. And he described in graduate studies, this is how he envisioned his future office. He would have, somebody would come into his office, I need the vapor pressure of something, something. He would say, 1 second, his words, walk over to the shelf, pull off the punch card box, feed it into a dedicated punch card reader connected directly to the McGill mainframe. And then the answer would come back right on his own dedicated ticker tape feeder. And he would be able to read off what the vapor pressure was according to the ticker tape. Like, this is what this stuff was designed for. Nowadays, we have more convenient ways. I'm not going to say better. I'm going to say more convenient. Categorically not better because it results in the exact same thing, actually. Okay. There is one more simplification. This is the way that's actually implemented in a lot of these packages. It's called the barycentric formula. Again, you do one more simplification. What you end up doing is noting that you require all of these to always equal 1. So you impose this other constraint onto this form. You require that the sum of these polynomials is always equal to 1, and then you divide through, and you've actually canceled your omega function entirely, right? Omega used to be this the product of all of these different polynomial terms. It turns out you can cancel that entirely. All you get is this, and it avoids this issue where x is close to one of these data points. So with the formulas up here, I know I'm jumping around a lot here, right? When x2 is close to x1, right? 1 over that number, that's going to be a small number. 1 over that number is going to be a large number, and you can run into numerical inaccuracies. The barycentric formula kind of avoids that by just canceling out those terms. Okay. Any questions on Lagrange polynomials? Typically, we're only ever going to deal with degree 1 or 2. That's all we're actually going to use moving forward. Newton's divided difference. Kind of complicated, kind of messy. It is what the difference engine was actually built to do. If you're interested in like the computational history of how these things worked, by all means, take a look through here. I'm going to skip it because otherwise I'm going to run out of time and we can't get to neural nets. One of the nice things about this is that adding, evaluating, and adding data can all be constructed recursively. That's the benefit to this guy. So if you start off with 3 data points and now you add a 4th data point, the difference engine is able to expand your third one to include another line that corresponds to your fourth one, and fifth, and sixth, and seventh, and eighth, and ninth. So you don't have to recompute everything, which again is really good when you're doing stuff like shuttle trajectory and you need an answer, right? That's what this stuff was for, right? Ballistics. You get a new data point. You want to fit your 30th order polynomial. Terrible idea, but you could, right? You don't want to recompute everything because then your click-clacks are going to be click-clacking the whole time. Okay, let's talk about the way that it's actually done nowadays, which is more of a direct method. So this is only really practical because linear systems became super easy to solve with computers. How do you solve linear systems? Don't make me go back. If I give you a linear system, what do you say? Huh? How do you solve linear systems, guys? I'm not moving past this until someone shows it. Gaussian. Okay, but what's the tool that you would actually use in the numerical method? What is the generalization, the abstraction of Gaussian elimination? Not sparse. It's not sparse. We're going to see that this one isn't sparse, right? Decomposition. Decomposition. Which kind? LU, right. These matrices will generally be small, and they're going to be ill-conditioned. If you have a small, ill-conditioned matrix, what's your go-to? One of you guys. Don't make me pick out computers. Let's go. Yeah. Use a solver? Yes. What kind? Would you use an iterative or direct? You sure? Why would you use direct? Apple computer in the back corner? Nothing? All right. Person in front of person with the apple, nothing? Come on. No, don't even need preconditioners. But preconditioners would improve the condition number, right? Kind of related to it. If you have an ill-conditioned matrix, your direct solves are very robust to ill-conditioned systems. So ill-conditioned systems are, again, they're the ones where the two lines are kind of touching, and if you throw an iterative solver on it, then you jump between these two. The direct solver is your go-to. It's the most robust. It's going to be able to find an answer, and that answer will probably actually be right, which is related to the reason why the iteratives don't work is that you are compounding the error every time you do the iteration. Okay? If you have a dense system, no. If you have a matrix which is ill-conditioned, your options are either go for a preconditioner first or throw a direct solver at it. But for small systems, direct is the way to go. I feel like I should ask the follow-up question. Why? Why do I keep saying for small systems? What happens when you go for large systems? Yes, why? For dense matrices. Quantify, please. You already answered. Hey? Well, yes, but how many more operations? And no, cubed. Yes, yes. If you remember nothing else from this course, dense direct solves n cubed. N cubed bad. Sparsity good. N cubed bad. But if you only have three, if you only have a 3 by 3, who cares? Throw it at your linear solver. It'll chunk through it. It's only when you get up to, 100 by 100 or something like that, that n cubed all of a sudden takes off. All right. Let's consider this polynomial. This is an n-1 degree an nth degree polynomial, right? We have all these guys. For a given xi, I guess I deleted this guy. What was this? 0 and 1. For a given xi, we're going to get, right? You plug this in. This is that xi. Blah, 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 blah. You're going to get your associated yi. This turns into, here's the leap. Your polynomial is a linear sum, a weighted linear sum of your monomials, right? This is one thing that, like, in linear algebra, I'm like, okay, polynomial, monomial, whatever, right? No. Here it is actually being useful, to be entirely honest. A polynomial by itself is is a point with a monomial function space. If that means anything to you guys. It probably would have 2 years ago after you did linear algebra. What that means is that you could actually write out for all of your data points a linear system. Like this. This becomes your bases. Okay? So these are the x's here. x0, x to the power of 0 is 1. 1, right? x1 over here, you just calculate that through. x1 squared, blah, 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 blah. You repeat that for all your different x values. This becomes your vector of weights. And this becomes your known measured values. How much more space do I have here? That's okay. Oh, no, I need to get through RBFs. Oh, and cubic splines, too. I'm going to be running into Thursday. Yes, thank you. Okay. If you don't believe me that it works out this way, just go through a couple rows, right? This is x1. So let's say x1 here. Do you want me to write this out, or can you guys follow along in your head? I feel like if I'm at, whenever I ask that question, I feel like I should do it. This doesn't have a funny thing above. All right. Y at x1 is equal to, let's just do 3, right? Y at x1 is going to be equal to a, what did I call this? A3 x1, sorry, a2 x1 squared, right? Plus a1 x1 plus a0 x1 to the power of 0, which just becomes 1, right? And this guy has to equal y1. Everybody see that? Repeat x2, the same a2, x2 squared, plus the same x1, x2, plus the same a0 is equal to y2. See where I'm going here? Right? A2, x3 squared plus a1, x3 plus a0 is equal to y3. If you don't see it yet, keep staring at it, and this will turn into a linear system. You've got your vector is a2, a1, a0. I think I've swapped the order of the lines there, but it doesn't really matter. Did I swap it? No, I didn't swap it, right? x1 squared, x1, 1. Okay, here I swapped it. I got it. Right? Again, doesn't really matter. Oh, yeah, because that order, right? x2 squared, x2, 1, x3 squared, x3, 1. And this is equal to this vector here. Should I turn on light? That help? Yeah. The matrix of these coefficients, right? So you actually evaluate this. You know beforehand what your, I erased it again. Can't be trusted with erasers here. You know what your vector, what your xi's are, because you have them from before. They are these guys. Was this 1, 2? Right? Those are these guys. So this guy actually gets written out numerically. There's no symbolism here. It's called the Vandermonde matrix. And you solve for this vector as a linear solve using, thank you. Okay. This system is notoriously ill-conditioned, right? Very, very, very bad. So you want the dense linear solvers to throw at it. Okay. So this is our example, and it's almost time to go. When we take our nice toy problem, our nice Gaussian, we throw it in here. I'll just show you. This is building it, right? We're building the Vandermonde matrix, and then we're even using the Legendre fit to work out these coefficients. Oh yeah, sorry. This is just using the Legendre polynomial fit. So because all of these guys only ever result in the exact same polynomial, right? You can just use any of them. Here, where is this from? NumPy? Yeah, I think it's the NumPy function that gives us a Legendre polynomial. We just use those. And this is our polynomial fit: 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have an 11th degree polynomial that fits all of our data points. Is this a good fit? Somebody? Yeah, right? It is only good, and I should make another example with this. It turns out that this is only good even in here because you have evenly spaced data. If you didn't have evenly spaced data, you would find a much different behavior. This kind of random or high frequency oscillations happens throughout the entire thing. It is an example of something called Runge's phenomena. I'm not sure if I'm pronouncing his name right, which states that even for a seemingly ideally case, high polynomials can show these huge oscillations. There are all kinds of reasons for this, amongst which is the conditioning of that Vandermonde matrix. We're going to get into all this with another one. Super quick, and then I'll let you guys go. For any endpoints, there is a unique polynomial that will fit those points. The problem is that you don't want to go too high. Low order polynomials are okay. Generally, you just throw a linear solver and you would do the Vandermonde matrix method to get the solution. But as soon as you go into higher order polynomials, Runge's phenomena kicks in and you get these high frequency oscillations. This summary belongs later on.
Okay, so that was fun. Last time, and we have to make up material too. Good. Tuesday is off, by the way. Truth and Reconciliation Day. All classes and assignments are canceled. So Tuesday, don't bother coming. Nobody will be here. This time for real, not just traffic. Monday is still on. We're going to start assignment 2. I'm going to show you assignment 2 tomorrow. Think about it over the weekend. You can come on Monday. You'll have time to do the comprehension quiz too. But if you are looking to take a long weekend and take advantage of Tuesday being off too, it's not mandatory to show up on the assignments. I did get some feedback. People are asking for the answers to assignment 1. I will post those either later today or tomorrow, and then you guys can take a look at them, and I'll go over them in Monday's lab section. That way we can talk about the results and things like that. Are these being posted online? I've been working to get them onto A2L now. Are your marks showing up there? Yes. So good news, A2L doesn't have geometric average. It doesn't even have square root. It has product, but what we're going to have to do is export everything to Excel, manually do it there, and then chuck it back in there. Okay, last time. We concluded the lecture, so we talked about polynomial interpolation. Remember again, interpolation is when your curve has to go through the data points. Of course, that has various fallacies. One of the biggest ones is when you get to higher order polynomials, especially near the end, but also sometimes it creeps into like not just the last interval, but also the internal intervals too. You get this effect called Runge's phenomenon. It's related to high frequency oscillations, tends to show up on higher order polynomials. And the bottom line with dealing with that one is thou shalt not do higher order polynomials. You want to stick to the low ones. Those are stiffer and that they don't do all this by, high frequency vibration in there. Okay, next up is cubic splines. So cubic splines were specifically designed to avoid all this oscillation associated with Runge's phenomenon. The idea is that we're going to fit a low-order polynomial between sections of the data, and then we're going to enforce continuity, right? So we've got 4 criteria. We've got y at x1 is y1, y at x2 is y2, and then we're going to say that it's continuous with the previous one, right? Both the first derivative, so by design, like this way, it is C0 continuous, in that you have, do you guys know those terms, C continuous? Ever heard of it? Yeah. So, by the first 2 points alone, if I have these 2 data points, say I have another one over here, right? I'm looking at this section. So I've got a curve, it's going to go from here to here, but the next one is also going to go from here to here, right? Therefore, this curve here is continuous. It goes from one straight into the other one. That one's called C0 continuity, in that it goes by the derivative. That's what they're talking about. C1 continuity is the first derivative, right? So this would be an example of C0 continuity, right? No problem because it's continuous. Not very smooth because you have a discontinuity in the slope. This is the non-differentiable function, right? So the next one would be C1. This is my artistic skills when I'm already late. I don't know why I'm doing it this way. Let's see. Something like that would be C0 and C1, but not really C2. Because this could be a nice downward facing parabola, and this could be a nice upward facing parabola, right? This isn't an inflection point. This isn't a cubic. This guy is what? Negative x squared. This guy over here is x squared. So if you look at the second derivative over here, this is -1. This is 1. Forgive my inability to differentiate between a cubic and to join quadratics at that point. The fact that the slope is continuous means that it's C1. And then the magic is it's also second derivative continuous. So now it's basically as smooth as like the human eye is able to detect, right? Okay. For constraints, what kind of polynomial is that? Don't have time, cubic. Right? 4 pieces of information, you can always fit an n-1 order polynomial. 4 minus 1, 3, you're into a cubic. Hence, piecewise cubic splines. So the idea is that at every point, we're going to fit a cubic between here and here, something that looks nice and smooth, and then over here, we're going to do another one, and that smoothness condition is what's going to make these things look nice. Everybody ever use Inkscape, for example, anything like that? Vector graphic imaging, a little bit, yeah. So if you, what's that? Yeah. If you look at, I don't really have time for this. If you're ever doing a graphic program and it's giving you something that looks like a curve, and all of a sudden there's a box here with these 2 guys sticking out the side, and like you drag this and it kind of does one of these over here, and it does like one of these. You do those angles. Does that mean anything to any of you guys? Right? A little bit, right? That's what you're doing. What you're doing here, these are called your knots, next section. And by adjusting those, you're adjusting the parameters of your spline curve. Back in the day, before they were computers, they had a little piece of plastic that was cut out into nice curves. It was called a French curve. I'm so old that I actually used a French curve back in the day, and you would just kind of like draw like that. Right. Anyway, back in the day when dinosaurs roamed the earth. All right. So we're going to describe these splines in terms of the knots, which parameterize the curves. There are different ways to do splines. I'm going to cover the most basic one. You will not need to know how to program in splines into NumPy and SciPy in this class because there's no point. There are 150 things, and it's not actually the one that I would recommend you dig into anyway. That would be RBFs. Okay. So in this case, your knots are the second derivative of your curve. I'm gonna slam through this stuff because I'm late, but all the notes are here. What you want to do is between each point here, you say that I have the second derivative at this guy. That's going to be your K0. Your second derivative at this guy, K1, and then the second derivative anywhere between here and here is the linear interpolation of these guys. What you do is you write through here, right? Pi and pi plus 1 is actually your Lagrange polynomial of degree 1. The super simple one, right? But you go back in your notes and you find that it's x minus x1 over, what is it? X1, no, sorry. X minus x1 over x1 minus x2, and the other one is the other way, right? I told you that these are going to keep popping up there. Okay, what you get when you calculate it through is you get something like that. You integrate this a couple times to solve your differential equation. You use your boundary conditions, and you get this nice formula, which is terrible. You repeat that for every single one of your data points. And lo and behold, what you get is a linear system. What kind of linear system is this? Yes, tridiagonal. It is sparse. It is symmetric. I'm fairly certain that's probably going to be symmetric positive definite. It is diagonally dominant. It is tridiagonal. How would you solve something like this? Yes, sparse solver. If you don't have that answer on the tip of your tongue by now, you fail assignment 1. Right? When you do that, sure enough, you get something that looks better. It's still not fantastic at the boundaries. Nor will it ever be fantastic at the boundaries. None of this deals, all these continuity conditions don't deal with anything at the boundaries. Boundaries are a perennial problem. There are different approaches to what you do at the boundary. This isn't in the notes, so this is just Mike talking. Right? One idea is to make everything periodic, but as soon as you make things periodic, you're questioning why you're not doing Fourier. Another option is to make it, what would you call it? Insulative, zero slope, right? You could just say that over here, this is constant. That's one option, or even better that the slope is 0, right? Because if this ended at a bit of an angle because of numerical noise, then your constant would have actually like a right angle at that point. So there are different ways to do this. All these things are kind of like standardized, to be entirely honest, and already in the packages, which is what I would suggest you use in this sort of thing. Cubic splines are generally stiffer. They don't have the high frequency oscillation. They avoid Runge's phenomenon because you are only ever dealing with a cubic polynomial, right? So this you have, okay, the data is actually kind of indicating that maybe you will go curve down that way. We know better, but if we didn't have this little tail here, if I didn't show that, maybe we wouldn't have known better, right? But it's not associated with this phenomenon emerging. Concept of smoothness is easy in 1D because we say it's continuous here and here. The first derivative is continuous here and therefore over here too. Second derivative also. What are you going to do in 2D? What's that? Talk to the professionals is a better answer. Partial differentials. Okay, that's one good way. There's another good way. You will know this very well by the time you finish undergrad. Cry. Right? 2D, there is an option, I think it's called B-splines, right? That work for particular cases for two-dimensional splines. They're used, I think, a lot in the automotive industry. That's what they were originally designed for designing all these nicely curved surfaces for aerodynamics, right? Because aerodynamics, computational multiphysics, all depends on the surfaces and the curvature and everything like that. How do you parameterize this when you're actually manufacturing these things at scale? You need these tools. That's what the splines are for. And the nice thing about a two-spline is that that's a surface in 3 space. After that, you're boned. There's nothing. The fact that you are implying smoothness suggests it's a little bit more of a global scheme as opposed to a local scheme. I'll come back to what it was. I'll show you guys. If I had this data point and this data point, the two easiest ways that I'm going to come to in the summary here. One of the easiest ways to do this in n dimensions is just to say whichever point I'm closest to, take that value. I am close to this value. This is the nearest neighbor. Clunk. That's my data point here, right? And in 3 space, in n space, in 1 million space, you can still do that. All you would need to do is find your nearest neighbor and take that value. Super fast, super generalizable. Problem with that one is that you have to find the nearest point, right? For regular grids and things like that, it's process triangulation. It has additional computational bulk in the meantime too, right? The alternative is called linear n-dimensional interpolation. Now you need to find the 2 nearest ones, draw a straight line, that's your value. You can generalize that to ND, but now you still need to triangulate what your nearest cloud of things are. As you get more and more and more information, right? Like this guy is not smooth. Terrible, terrible smoothness. The nearest neighbor doesn't work at all. Practical, but it's terribly not smooth. Linear is a little bit better, but you're going to get faceting, right? So if you're playing video games and you zoom in too far and you see like all the polygonal surfaces and stuff, what you're seeing is basically linear three-dimensional interpolation. And it looks kind of smooth if you have enough triangles, right? But otherwise it's going to be really clunky. The concept of as you want to get smoother and smoother and smoother, you're expanding your domain of points that you're considering in your local interpolation, which means you are moving more and more and more into the realm of simultaneous solutions and linear systems, right? Well, if you try and fit a single polynomial to all of your data, then you've got the entire thing. And you've got to consider the entire thing, and now you're into a dense matrix. Right? When we did the monomial expansion and solving for that direct system, we had to do a dense matrix for the entire thing, which was numerically unstable. As you localize and you bring that in more and more, right? Cubic spline kind of localizes in the data that you're using to fit that polynomial. Now you are making the matrix more and more and more sparse. This guy is diagonal. There's no sparsity whatsoever. Linear, but then there are other challenges associated with that. Questions so far? Okay, that's kind of like what all this like matrix density is really doing. It's how much the information at one point depends on the information around it. Okay, RBFs are something you'll probably encounter out in the wild, which is good. I'm always happy like when we actually get to something that you guys could actually walk away with using, because a lot of the time I can't get that far. Calling me. Okay, RBFs are n-dimensional. Fantastic. Doesn't rely on polynomials. Fantastic. Rather, we define what's called a radial basis function. It's called a kernel, and it's applied to each data point. So the idea with this one, can you guys, I'm going to turn off this. So this kernel is a function of, do you guys remember what this is? Norm, right? Which is the default kind of norm. Euclidean norm, Pythagorean norm. It is the distance, right? This is why it's called the radial basis function, because the function depends only on the radius between your data point and the point of your evaluation. X, your point that you're evaluating at, and your data point xi. Okay, so it's spherical when you look at this thing. Commonly, right, we're going to say that phi I, the radial basis kernel, at x1 is equal to 1. We saw this already with, which was it, the Lagrange polynomials. When you do this, it simplifies a whole bunch of the calculations. But it's just kind of like a nice reference. You don't have to do that. It just makes it a bit easier to look at the numbers. What we're going to do is we're going to say that the overall function is the weighted sum of all of your RBFs. So for every data point that you have, this is the interpolation part. For every data point, you're going to have an RBF associated with it. Most common kernel is a Gaussian kernel, right? Which is going to look something like this. At every data point, you're going to have a Gaussian kernel, right? And your overall function is going to be the sum of all of those kernels associated with their data points weighted by some weighting factor. So we're back to the weighted sum again. I'll save that kicker for the end. Okay. To determine the weights, we just use the data points we have. So our overall function at xi is the weighted sum, which has got to equal the data that we have, the yi. When we apply that to all of our system, we get a linear system again, right? Surprise, everything's coming back to linear systems. That meme in the beginning, Leon's meme, wasn't wrong. It does all boil down to this. Okay. I understand if this looks a bit formidable. stare at it a little bit, see how the code builds it, right? It's going to become, it's actually pretty easy. It's kind of a neat way that it works. Okay, so this matrix is evaluated. This matrix captures like the spatial dependence, the x dependence. Your weighting constants is your unknown vector. Typically, we talk about like ax is. I have this later. Previously, we did this. Ax is equal to b, and we solve for x, right? With RBFs, also the monomial thing, the Vandermonde matrix, right? We didn't have that. What we actually had was a as a function of x. Omega was our vector. Okay, it's a little bit of a twist. I just want to raise the awareness of that. Does that make sense? So we're moving the x dependence into the construction of the A matrix. Our unknown vector is actually the vector of weights. And the nice thing about this is that we know how to solve this. Okay, when does a Gaussian go to 0? Never. Which means, so there are different kinds of kernels. Here are some of them. There are other ones. A lot of them, a large class of them will approach 0 as you move away from your data point. In other words, here, this guy goes to 0. It never gets to 0, but it at least gets small. And what that means is that data, the interpolation evaluated over here is going to depend very little on this guy, right? Because this guy's influence is going to be right around 0. Whereas this guy is going to have a much larger influence. That's the idea. That's kind of like the underlying thought with this. Your interpolated data should depend most on your nearest data point, which kind of makes sense. If you're walking on, so there's another technique called kriging. This guy gets us into like surrogate models. If anybody's looking for a topic for a research project, look up kriging. It's also kind of interesting. Or Gaussian emulators is another thing. Cutting edge. They're all over the nuclear field. Hey, right? They're also very big into geological surveys. Apparently, that's where like they were originally developed. The idea is that if you're on a mountain, running out of space here. If you're on a mountain, you know how high this point is. You know how high this point is, and you want to know how high this point is. Right? Is it going to be approximately 10? Or is it going to be approximately 1? Obviously, right? Whatever data point is closer is obviously going to have more, it's going to be more similar to the closer data points, right? If you had another data point over here, a pretty good approximation at this point would actually just be a linear, it would just be a straight line, right? A hell of a lot better than saying 1 and minus infinity over here because you're in a cliff. Some nonsense, right? So there is logic behind all this stuff. Okay, I'm just going to show you what these guys look like first. So all these three all have this property that they approach 0. They don't get to 0, but they approach 0. Yeah. Yep. Yep. Absolutely no idea. Very good reasons exist. They are all way beyond me, to be entirely frank. Wikipedia is one of the best ones. This is very well centered into the range of machine learning. As soon as you talk about machine learning, you have to talk about hyperparameters. Your hyperparameter in this case is the width of your Gaussian. So we know that it's a Gaussian. Our weights control the height of it, right? What we don't know is the full width at half max, if you guys are familiar with that term, right? That property is considered a hyperparameter of this model. And there is not a great way to figure it out. You kind of have to play with it. right? And this is so different because different kernels will have different dependencies on their hyperparameters, right? But then there's more into it when we get into this stuff. It is very nuanced. I'll show you what happens when you don't choose the right one, right? A good rule of thumb is apparently, and I say apparently, I'll show you why in 5 minutes, 1 over the average distance. And you can kind of see why, right? Like the whole idea of RBFs is that you share the information from here elsewhere. How wide you want that influence to spread kind of probably has something to do with the spatial distance between all those different points. That being said, doesn't work well. Unfortunately, if any of these nice kernels actually went to 0, I'll come back to epsilon in a second. This guy is not 0. This guy is approximately 0. That's the nature of Gaussian. Same with these guys. If it actually did get to 0, then you would be able to kill some of these terms. Then you would be able to get a sparse matrix. And matrix sparsity is the gold. That's what we want. Unfortunately, the vanilla ones don't have that 0 property. Some ones, I think they're called pancakes. I think in SciPy they're called like pancake or something like that. They are the imposed, like they'll have something that looks like that and then a cutoff. And it just cuts. And what that means is that I think it's the neighbor parameter they call it, right? What that means is that you end up with a sparse matrix when you're doing this. The more data points you have, the more rows and columns you're going to have on your matrix. For a dense matrix, we're going to solve it using LU, right? How many operations is it going to take? N cubed, yes. There you go, right? N cubed, good or bad? Okay. Good thing we have iterative, right? Okay, so this is an example. You can load up. Remember, you can go to the Rocket Ship and load this up in Colab. And I think we're going to have to actually, because it doesn't work very well for some reason. It's not displaying on this. When you plot this, here is the matrix that you end up building. This 0 is not a true 0. I'm telling you right now, this is NumPy formatting. Yeah, tell me about it. This is NumPy formatting that's showing this at 0. You can tell because looking at this, like it's definitely not 2 decimal points in all cases, right? So don't trust your 0 either. When you do the inversion, sure enough, you get this beautiful creature, which is awesome, right? It even goes to 0 out here. This is only a property because our function, our true function, actually goes to 0 out here. In general, it's not going to, and you're going to need your curve fitting thing. That's maybe tomorrow's lecture, assuming I get here in time. Is this actually going to show? No, it's not. Okay, I have no idea what was going on with this. I was messing around with this for like an hour yesterday. Loading, loading, loading. Run all. Yes, run anyway. Okay. Here's all the code. Feel free to go in, look at it, see how those matrices are built. 2D Gaussian. A lot more code with that one. So this is using a true function that looks like this, right? This is a Gaussian true function times a sine times a cos. Doesn't really matter. It looks like this. Okay, and then we're sampling it over all these randomly selected points. We're going to take those points and then try and fit the Gaussian to it. When we do, we get something that looks pretty decent, but still has something that looks an awful lot like Runge's phenomenon out here, right? This is not Runge's phenomenon. Later in the curve fitting part, we're going to get into what exactly this is. This is actually numerical instability. This is because that matrix, that phi matrix that we built, has terrible conditioning. The condition number for that thing is like 1e16, which is awful, right? It's just disgusting. And the influence from that is from actually your epsilon, from your hyperparameter, which is again goes into why you would choose that epsilon, why you would choose different kernels, etc., etc., etc. Notice though that this is not just continuous, this is absolutely continuous. Gaussian profiles and a sum of Gaussian profiles are infinitely differentiable. So they have C0, C1, 2, 3, 4, all the way down to infinity continuity. They are absolutely continuous, which can be nice. Just to show you an example of what happens when you choose epsilon. So remember how bad that one looked like. Where's my line? So this is choosing epsilon to be 1 over the average distance. If instead we just say epsilon is 1 and rerun it, yeah, there you go. All of a sudden, this thing looks a whole lot better. This is the fit, right? So unfortunately, this gets into, there are reasons why one epsilon would work better than another. There are reasons why one kernel would work better than another. But this is kind of where like the human intelligence has to step in, right? And say, would you expect an interpolation ever to do la 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 la, right? Like, no. All right. Caution for blind listening to this stuff. All right. Oh boy. I was trying to finish this yesterday on Tuesday. Talk about this stuff. Yeah, no, thank you. In 15 minutes, I've got another meeting. All right, good. All right. Polynomial interpolation, splines, RBFs, they can all be expressed in terms of a linear function basis. What the hell does that mean? What that means is that your overall function, y, erasers are for suckers. Okay. If anybody ever knows Professor Oforiopoku in material science, we worked together at CNL. He always got really pissed off at me because I couldn't be bothered to erase my whiteboard, so I just took a different color and wrote on top of it. It worked for me. Okay. Whenever you have something like this, y is equal to the sum of blah times pick something, fi. This is like this weighted sum. When something is equal to a weighted sum, this is actually what a linear function basis is. This becomes your basis for the function space. This becomes your coordinates, right? In a way that you can kind of quickly imagine that is you could say my point y is equal to a x hat. Do you guys use hat? Okay, you know what I mean, right? 1, 0, 0, right? Plus A2, 0, 1, 0, plus A3, blah, 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 right? This is your vector basis, right? Otherwise known as a function basis. Function is the generalization of the vector for certain cases, right? So it's kind of the same idea, but what that implies is that you can throw linear methods at it, right? And when you're doing that, your functional dependence goes into your matrix, but your weighting vector is what actually determines how your fit is going to behave. And this is fantastic because we know how to solve this type of system. This is b is equal to a times x, right? We've shifted the notation now. It's y is equal to a times omega. A of x, functional dependence. For me, all these round brackets are all functional dependencies. By the way, I like square brackets for grouping terms, round brackets for functional dependence. Okay. This is good because we know how to do this. So to recap, for any endpoints, there's a polynomial that fits that exactly, right? But you don't want to use the higher order ones because of Runge phenomenon. Piecewise polynomials are stiffer, they avoid Runges, but they don't generalize, right? RBFs are neat, not reat, and flexible, but they're prone to numerical error because this condition, this matrix condition number, ends up being terrible. And you also have this other degree of freedom associated with your hyperparameter. I think technically the choice of kernel is also considered a hyperparameter, but that's like a whole other level of abstraction. Okay. One pragmatic possibility, I talked about this, right? Pragmatically, what you could do in n dimensions is just say, I'm here, where's my nearest neighbor? I take your value. Or you could do one up on that and say, okay, where's my total cloud of nearest neighbors within some radius, and I am the linear interpolation of these guys, and lo and behold, you're into one of these polyhedral meshes that you see in video games and everything. Okay, I've got 2 minutes. I'm just going to quickly introduce you guys to this so that you start thinking about it. Curve fitting. We have some data points. We don't need to go through all of them. Instead, we have 10 data points and 2 parameters. We need the best fit for those 2 parameters, right? In terms of those data points. The way we're going to do that is we're going to define our residual, right? So our interpolation function is a function of space. That's fine. I'm also going to say that it's a function of our parameters. And that's a little bit of a weird way to think about it. It's actually very profound, and like there's a field of study that goes into this. It's called adjoint methods. Okay, but just trust me, guy. Omega or y is equal to a function of your parameters as well as your basis functions, your x dependence. Okay, the best fit is defined when you have the minimum of your residual vector. The minimum of a vector. Nasty. We don't like to talk about that. So instead, what do we say? Residual is, instead of looking at the entire residual vector, we look at the norm of that vector, right? Again, we're just throwing Pythagorean norm on it, right? So the whole goal is to minimize this R. In general, this is an optimization problem. Optimization won't be for another 2 weeks, so I'm skipping ahead a little bit. You're going to see why. What we're going to do is we're going to extend everything that we've talked about for interpolation almost verbatim to curve fitting. And we're going to do that through a magical thing called the pseudo-inverse, which honestly is mind-blowing that this thing even exists. This is actually really cool. But I am out of time. Nonlinear least squares is more complicated. We'll be covering that in the optimization chapter. So starting on tomorrow, pseudo-inverse. Oh. Guys, is the next assignment on, has that been released to you guys? Can you guys see that now? Yeah, okay. Good enough. I'll take that. Okay, let me get through this and then we'll talk about that. There's a chance that I might need to jump over to another meeting, but somebody will let me know if I do. Okay, so we're talking about something really, what I thought this was a whiteboard. Aha, tricky. Well, that's generous. Okay. So today we're talking about something really cool called the pseudo-inverse. It's going to broaden our abilities to adapt all these interpolation techniques to curve fitting techniques. The way it works is, say that you have a linear system, AX is equal to B, but now you're no longer requiring A to be a square matrix. Now it can be rectangular. In general, it's considered M by N. My coffee cup is leaking. That's funny. Chug, 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 chug. All right. In general, A is M by N. X is N, which means that B is M, right? Which way, if it's rectangular long or rectangular wide, actually has a lot of impact for what the pseudo-inverse means. Generally speaking, though, we're going to end up with the long version. That's the one that we're going to recover when we have more data than we do and more information than we do parameters that we're going to want to fit. Okay? Because X is the length of the parameter step. Oh yeah. So the way that it works, the way that you can derive this thing is you define what your residual vector is, right? AX minus B, just move it over onto the other side. And what we're going to say is that we want to minimize the norm of the Euclidean norm of R. Okay? So this R is just, of course, the square root of this dot product, standard Pythagoras, right? And what this is equivalent to is finding the minimum of this quadratic, right? When you do that, you take the vector derivative. The nice thing about linear algebra is that vector derivatives actually work almost exactly like you would expect as an extension from regular derivatives. So you can just do that. You get this form, right? Because you take the derivative of, what is it? The first here, that transpose goes in there. You get AX minus B. The same thing happens on the other one, but now in the transpose. So you have to flip it back, which you can do. And you get 2 times that, and it just cancels out the 2 there. Okay. You do some simplification here. You move this over to one side. You multiply through by the inverse of A transpose A. And now you get this funny equation here. I don't really have time to go through step by step, but this is the way it works out. And we're going to define this as the pseudo-inverse. And the nice thing about this is that it's defined for any rectangular matrix. And all the inversion, oh, that doesn't really come through at all. Look on your screen. There's a -1 here. A transpose A is a rectangular times a rectangular of same dimensions, just transposed. It's always square. So you can always do this guy through standard like LU decomposition because that's how we're inverting these things, right? In general, as word of warning, that is not how the pseudo-inverse is actually calculated. Again, it's this eigenvalue, singular value decomposition that's manipulated around and chucked back into this thing. So like if you look into the documentation for least squares fitting in NumPy, SciPy, pseudo-inverse calculation, it's going to talk about like arcond, for example, is an option that it gives. And that's the threshold from which a singular value, an eigenvalue, is considered non-zero, right? Just saying that part's not on the test, right? Just if you use it and all of a sudden you see it spitting out something about arcond and this and this and this, it's because that's what it's actually using, but it doesn't change the function of these things. Okay. Bit of terminology. This probably a review for most of you guys. So a consistent system, right, is where you have the 2 lines that intersect in exactly one point. An inconsistent system has multiple equations. And what we're going to see is that they can, do I have an example? Do I need to draw this? Here we go. This is the consistent system. I'll come back to it. You have 3 equations, but they all have the same solution. No problem. Right? An inconsistent system, you have more equations than unknown, right? And this is basically always what you're going to be dealing with, to be entirely honest. You have more data than you have parameters that you're going to be wanting to fit to it. There is no simultaneous solution, so there is no solution to this one, but you can find the best fit. And we're going to define what that best, actually we already defined what the best fit was. The best fit is the solution X that minimizes R. And that solution is given exactly by this equation, which is really nice. Did you guys do linear regression in like first year by way of like lab analysis and like fitting polynomials and stuff like that? That's where I did it. Have you guys done linear regression at all? Just Excel, right? Yeah. How do you do it in Excel? That's how I did it in Excel too. Yeah. It's like goal seek or something, right? Or a little function. Yes, yeah, well that's yes. Okay, yeah. Yeah. Right? This is what it's doing in the background, right? The alternative is just doing a standard minimizer optimization routine, but it's possible, but it doesn't really leverage all this numerical all these linear system techniques that we're developing here. Okay. An underdetermined system is when you have fewer equations than unknowns. Can you find a solution if you have 2 equations and 3 unknowns? Anybody? Who says no? Right? Now, yeah. So if you have, so let me give you guys an example here. This is why I'm constantly late. I'm always giving examples. Let's say I had x plus 2y plus 3z is equal to 1. And now I have 2x minus 1y plus 4z is equal to 2. Can I find a solution for x, y, and z? Who says no? Okay. Who says yes? Yes is actually correct. There is a solution. Of course you can't. Of course you can't. But the pseudo-inverse will. And this is the danger. This is the danger with package tools and these techniques. This is why I didn't introduce pseudo-inverse earlier. It turns out that if you throw this into pseudo-inverse, it will come up with an answer. And that answer is bafflingly the answer for which the norm of that answer is minimized. Normally with pseudo-inverse, we're minimizing the residual, i.e. we're trying to find the best solution. But if you throw one that is underdetermined like this, where obviously, you cannot possibly find x, y, z that satisfies this. But pseudo-inverse still will. But now this answer doesn't mean what you think it means. This is an answer that is a very particular case. It minimizes the norm of that answer vector. But of course, that's not the only answer. Right? This is an answer to this, but there are many other answers too. You guys won't come across this in this course anyway. This is more of an advanced linear algebra topic that you guys would get into this sort of stuff, but just to throw that out there. If you throw it at an undetermined system like this, you will still get an answer. It just doesn't mean what you think it means. So with that, we're not going to talk about that one anymore. By the way, that's all about null spaces. It happens to be that the directions that you can expand and you can still move your degrees of freedom are actually the null space of the original operator, which is just kind of like it's next level sort of stuff. So don't worry about that. Let's see how we can use this. First of all, properties of the pseudo-inverse. Pseudo-inverse is defined for any rectangular matrix. Overdetermined, underdetermined, is a square a type of rectangle? Yes, right? Therefore, a pseudo-inverse is also defined for square matrices. Okay? What is the ultimate minimum of this residual vector? Where's my residual vector? You guys have been answering questions. I'm going to go back into this clump here. What is the smallest residual vector I could ever get? It would just be 0, right? 0 means that you have solved the solution exactly, in which case your pseudo-inverse is exactly your regular inverse. So the most robust implementations of these things just throws it straight into the pseudo-inverse, because in the case that it is square, pseudo-inverse is going to find it anyway. However, it is more computationally complex. Right? Because it's using different algorithms that are a bit more robust. That's why in general they are separated like that for convenience. But if you were just like making your own thing, you didn't care about like 3 seconds versus 2, just throw pseudo-inverse at it. Okay. It also is nice because it generalizes a lot of the ideas that we've already developed. Like that's why I really like it. Because we take everything that we've already done for linear systems, and now we just add this dagger instead of -1, and all of a sudden everything still jives, right? The condition number. for a matrix. You cannot find the determinant of a rectangular matrix. Doesn't exist. But you can find the pseudo-inverse. So the condition number, all you do is you go through and wherever you saw inverse, you slap on a dagger and all the exact same implications apply, which is fantastic. Super convenient. Okay, there is a subtlety. Let's find it. There's always subtleties. There's always two edges to the sword. Okay, let's return back to our original tables and chairs example. I'm still debating whether or not to move this into like the first section where we first talk about linear systems, but I'll come back to that one afterwards. Okay, so what is it? $20 per chair, $50 per table, 700 budget. Total number of items is 20. I don't know, 50 minutes to make a chair, 20 minutes to make a table. Like insert justification for this question here. Okay, and you get down here, you get a rectangular matrix, right? Let's plot it first of all, and I already showed you guys these plots. Where's the solution? Obviously. Okay? Hasn't changed. Plug in your arrays. And if you try and throw a regular linear solver, of course, it will die. Because you're trying to do a square matrix solver on a non-square matrix. Right? That's what this is saying, but it doesn't tell you that. It says, what is this? Oh, well, okay, it does actually. The last two dimensions of the array must be square. There you go. Doesn't help. Now let's do the pseudo-inverse. So that's a matrix, that's a vector, right? Notice that all the pseudo-inverse isn't applying to the right-hand side. It's not, it doesn't care about that b. Again, we're separating out the function of these operators. Okay? We can just do the inverse of a dot t transpose. Do you guys know this what do you call it? The mouse face? I think the at symbol, I think in Russian is the mouse face. That's what they call it. I love that. Right? So this is matrix product, right? So A, you do the inverse because that's squared, that's kosher, right? And then you apply that to the transpose of A again. And if you spit it out, manual calculation is this, doesn't mean anything, right? But if you look at the inverse, the P inverse, right? Pseudo inverse of A, it spits out the exact same thing down here. And then if you actually, this is the difference, you know, remember everything like less than 1e minus 16 is effectively 0. So 0, 0, 0, 0, 0, these two things are the same. And the best fit solution is 10, 10, which is what we would expect. Okay, the package implementations for this, there's the P inverse is under the NumPy package. Otherwise, there's LSTSQ, least squares, right? That is the linear solver version. Remember, we very rarely ever want to store the inverse of a matrix because, yes, any sparsity is nerfed. Okay. Overdetermined, inconsistent linear system. Let's reconstruct this a little bit. We won't care about the justification this time, okay? So we've got these three equations. These are not all going to meet at a single line. This is the, okay, so that's the inverse, right? We don't actually need that. We can actually just calculate the least squares directly, and then we're going to plot it. These are our lines. 1, 2, 3. And the best fit solution is here. Is this what you guys were expecting? Anybody? Where were you expecting? Anybody? No? Are you expecting over here? No. Why? Why wouldn't you expect it over here? Back 2 rows. Somebody from the back 2 rows. Volunteer, or I'm going to pick somebody. Meeny, miny, moe, catch a tiger by the toe, you. Why wouldn't you expect a solution out here? Yeah, it's not even close, right? What do you expect it over here? You think somewhere in here? What about inside? That's where it is, therefore that's what I should say. That is a very, very good, like, passing the course answer. You want it inside somewhere because that's going to be the closest to. So there are two things. A lot of people will look at this and they'll think that you want to balance between these points of intersection, right? And you could be forgiven by thinking that, right? It turns out that what it's actually doing is it's minimizing the perpendicular direction from these lines, right? So that guy, that guy, that guy is actually what's being minimized. That is actually the meaning of what this residual calculation is, right? You would have to go through like a day worth of algebra before that would become obvious. So don't worry about that one. Okay, let's do another one. We're back to our original coefficients, blah, 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 blah. Where do you think the solution is going to be on here? I'm going to be coming over here. I'm telling you guys right now. Where? This one? You already skipped ahead, didn't you? Up here? Like here? Yeah. Da, 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 da. You plot it and kaboom. What the heck? Right? Twist. What a twist. I forget when that one came out. What a shock. I don't know. You guys probably weren't born yet or something like that. All right. What the heck happened there? We have something interesting. So last year, one of the students online had Pikachu as their avatar, and like I went online to call them, and I was like, Pikachu, I choose you, Pikachu. And I thought, like, yes, I have like a young thing. I'm still young at heart. And somebody in the audience was like, we weren't born when Pikachu came out, right? Like, damn it. Okay. Okay, so something else weird is going on here. And if you were looking carefully, you might have noticed that something was weird about this one compared to the other ones. 2, 1, 1, 1, 1, 2, the coefficients. And all of a sudden here, 20, 50, 1, 1, 60, 20. This gets into the notion of weights and introduces us into the weighted least squares, which is an extension of the one that you're actually going to encounter. Okay. As a general rule, with any kind of approximate methods, like it's kind of implied, right? Approximate means that you're going to be sacrificing something. And whenever you sacrifice something, there's going to be some kind of dial associated with that something that you can turn up and down. And it's going to be like kind of user's choice with vague directions of how to turn those dials up and down in order to get a solution. In this case, sorry, 1 second. Oh, never mind. Okay, cool stuff. Yeah, okay. In this case, what we were doing was minimizing the residuals. And there's something funny with the calculation of the residuals that you guys actually already played around with in assignment 1, almost by like design. Anybody remember? It's like super ultra bonus points here. What was the last question of assignment 1? Preconditioners, right? Does preconditioners change your answer? No. Doesn't change your answer. It shouldn't have changed your answer. Right? What you are doing with the preconditioner is you are changing the form of those equations. Specifically with Jacobi preconditioning, the diagonal preconditioning, all you were doing was effectively multiplying through an equation by a constant. So the difference between this equation, this system, and this system is exactly nothing. They have the exact same solution. The only difference is that your coefficients here are different. You could divide through, right? Exactly the same solution. It don't enter into it. That one's a super old reference. That's Monty Python, traditional. Okay, this is Jacobi preconditioning. That was old when I was young. Okay, this is Jacobi preconditioning. think about that connection a little bit. Like, take a look at this, go back to how I defined the preconditioner, and you'll see that that's actually super trivial to understand, right? But the idea is that we now introduce weight. And these weights are going to be the weight for which that we prescribe importance to those particular equations. And the idea is, if certain equations, there are two ways to look at this. One way is, it is super important to have exactly $700 spent. Super important. You absolutely have to have $700 spent. 20 furniture items, rough suggestion. Try and get it done, but it's super important to do 700, right? Therefore, you would have a heavier weight on this equation than you would the other guys. You could still satisfy it, but it's really important that you hit this number well. The other way is to say, well, look, we're kind of mixing magnitudes here. Wouldn't it be great to normalize things, right? And you can also look at it through that lens. So you can either skew your system to favor one of these equations or normalize it so that it gets to a better answer. Yeah. Effectively, yes. We are favoring the importance of one equation over another. The direct connection is when we're fitting data. If we have data that looks like this, right? So this is our well, okay. Getting ahead of myself here. Here's one data point. Here's another data point. This is our mean. This is our mean. It's a straight line. Which of those two data points are you trusting more? Right? Just because this one is kind of wacky-cacky, right? Technically, the mean is still there, but right? So what we're going to see, that's a technical term, right? What we're going to use the weights for is to weight data by its variance. And then you just chuck that into your system, assignment 2, right? And now you have your formula for your weights, which gives you actually a statistically quantifiably better answer by doing it that way. Does that help? All right. We say the residuals can be weighted, i.e. the least squares problem becomes blah, blah. When you code it, what ends up happening is, so there are a few different ways that you could define these weights, right? If you go the preconditioner route, the easiest way is to just define this matrix, right? This is diagonal. You guys all did this for assignment 1, or your buddy did it, or AI did it, but you took ownership for it, theoretically, right? You've got 171. That guy goes through and multiplies all of these lines in your matrix, and then you throw it into your least square solver. Okay? So it comes out to that, and now so that 171 is effectively multiplying this middle equation by 7. Right? Where does that number 7 come from? I made it up to give it a pretty plot. It could be anything. And all of a sudden, this dot has moved from over here all the way to over here. It is a little bit tricky. Again, lots of tricks, right? Lots of hidden assumptions, default assumptions. This is, I would argue, this isn't even like a default package implementation. This is actually like what the math is doing when you're not paying attention. The reason why it was down here and not anywhere close to the orange line is because the green and the blue were bigger equations. 20, 50, 60, 20, you can consider the norm of that vector versus 1, 1. And just by evening that playing field, you move it towards the middle. So if you didn't know about weights and you just plotted this thing and you just hit here, you would have thought that your algorithm was working wrong because it wasn't anywhere close to the orange line. And in fact, it was just answering not quite the same question. No, It was answering exactly the question you asked, not the question you meant to ask. Any questions? Okay. Let's move on. Oh, wait a second. I think I skipped part. Yeah, here we go. Okay. So weights are an excellent way to introduce uncertainty into your fits. What you do is if you have multiple measurements, right, you just ask for the mean. Mean, average, super easy to calculate. You calculate its variance. This is how you calculate the variance, right? Square of the standard deviation, otherwise known as dot VAR, right, of your vector, of the multiple things. Again, assignment 2. And then your weights are 1 over that variance. When you go into a package, right, it's going to have different ways to input that variance. I'm telling you right now, I cannot give you a good way to do it. It depends on the implementation. Read the documentation. I'm going to say that again. Read the documentation. Don't trust your buddy. Don't trust your neighbor. Don't trust the guy last year, right? Not that you guys would ever talk to the previous cohort, right? Don't trust AI. AI doesn't know this unless you ask it for it, right? But if you just vanilla ask it to do something, it's just going to do it, and it won't necessarily understand all the subtleties of this. Read the documentation. It takes like 5 seconds. And it's word of advice. Somebody who's been in this game 20 years at this point. 10 minutes to read the documentation is always going to be more efficient than 5 hours trying to figure out why the hell your answer doesn't match up. Always, 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 always. General case. Okay. Returning to polyfits. They threw something against that wall. It's like reflecting light off it. Party room or something. Okay. How do we, it's like seeing stuff. Hey, look, fuzzy bunny. Okay. How are we going to apply this to our other interpolation techniques? Do you guys remember what the other interpolation techniques we used were? Running out of time again. So I'm just going to give you guys the answer. There was a polynomial fit. You remember how we solved that one? We constructed the matrix of monomials and then we inverted it. And we also have the RBFs that I'll get back to in a second. Okay. So the idea was, if you don't remember this, just go back in the notes. Don't really have time for this. You invert. Now, all these lines is the amount of data that you have. So if you have 10 data points and you're trying to fit a quadratic, now you're into the realm of weighted least squares, right? Least squares approximation, linear regression. Let's do that. So we're going to generate a super messy function, data all over the place, right? Right? Do you want, how many data points is this, 100? Could you fit a 100th degree polynomial? Yes. Do you want to? Don't. It's terrible. Okay. What you want to do, you can follow through the implementation here. You want to define your Vandermonde matrix. That's a matrix of monomial things. And you can fit, in a best fit sense, the coefficients for this quadratic. And here it is. And if you look through here, there's no loops. There's no iterations. This is, technically, it is an optimization thing, but it's not like a looping iterative optimizer thing. This is like a direct solution that just gives you the best fit, quantifiably best fit quadratic to this. We could fit a series of best fit polynomials, right? So this is, what did I say? Something like 100 data points. That doesn't look like 100. There's a lot of data points, right? Y quadratic. Y quadratic and not something else. We can look at the somethings else. This is what you get for a full series of them. But if you look at the norm of the residuals, right? What you're going to see is that, so degree 0 polynomial is a constant. Degree 1 is a line. Is this a line? No, obviously. Well, there is the line, actually. There's your straight line. There's also the degree 0, right? Obviously, the quadratic is pretty good, and you can already see that in the residual norm. Sorry, this one's a quadratic, right? Once you get up to cubic, all of a sudden you plateau awfully quick. And actually, this was originally generated by a quartic polynomial. And interestingly enough, the residual norm starts to plateau right after the degree 4. Not a coincidence. So if you were really looking at this data, this would actually be a very good indication that you found a good thing to work at. However, if you add, that's this note down here. If you add on a little bit of extra polynomial degree, you are always going to get a better answer. Always. Just by adding on more polynomial expansions, you're going to get a little more wiggle, and it's going to match the data a little bit better. That's why this never levels off. This is asymptotic. It'll keep going until it will eventually hit 0. Sorry, it's not asymptotic. It will eventually hit 0, but that's at the order 50 polynomial, which isn't actually useful, or 100 or whatever it is. Okay. There's a problem. Again, always problems, right? The condition number of the Vermond matrix plummets. Actually, it dramatically increases. It goes off into space. The degree 1, the constant, right? 4, 3, not bad, right? Once you get up to the larger and larger n degrees, the condition number of that matrix that you're inverting goes off into the stratosphere. What's the optimal condition number? 1, right. Is this a good condition number? No. What do you think is going to happen when we get up to the degree 51? It's going to be massive, which is strange. It's strange because there is exactly one polynomial, degree 50 polynomial or degree 100 polynomial that exactly matches all those data points. But even if you did want to find that thing, the numerics are such that it would laugh at you. And it would be notoriously terribly unproductive. This is why low-order polynomials are so much more stable. And this is purely a factor. We haven't changed the data. We haven't done anything. All we've done is increase the number of degrees in that polynomial, the number of terms that we're fitting, the coefficients that we're fitting, the size of that matrix. And just by even increasing the size of the matrix, we haven't actually solved the matrix, just increasing the size of it, we get all this numerical error rumbling in. Question? No. Unfortunately. Yes. Effectively. This is why, I mean, numerical errors, numerical methods as a whole are an approximate, right? Just by definition. And whenever you're doing the approximate, you're going to have like the knobs and the dials, right? There was a question, actually, we're going to get to that about the epsilon, the hyperparameter in the RBFs and the radial basis function. How do you even know what kernel to use, let alone what hyperparameter to use? There are always going to be pitfalls. And that's one of the reasons why we can't just ask you for an exact answer on the assignment, because you're never going to get an exact answer. Column solve, there is no exact answer. There's only good enough. And can you defend why it's that way? And that's kind of the important thing. Or the other way around. If somebody asks you to generate something that's completely wrong, right? Can you say, no, obviously? Yeah. Okay. Coming back to RBFs, right? Last time we talked about so RBFs, again, there's this idea of this kernel. I want to speed through this so I have a bit of time for the assignment. The modern implementation, the one you're going to find in SciPy, is going to look something more like this. Actually, it's like this. the idea is, excuse me, that you're going to, because we're not kind of constrained to going through every single data point, we're actually going to combine two techniques. So we're going to take, so the previous RBF that we looked at was this data for a Gaussian, and sure enough, it followed that without a problem. And I told you the only reason that it looks so good at the size here is that the RBFs actually go to 0 over here anyway, and the sum of 0 is still 0. If you have data that is looking like that, and you go and fit the RBF kind of the way that we did it previously, you're going to get something funny because it's going to try and go back to 0 over here. So the idea with the modern implementation is you look at your data and you fit a super low order polynomial to establish the general trend of this data. So when you go into SciPy and you look at the things, there's going to be a parameter called degree. That's the degree of this best fit polynomial that you're using to baseline things. And then everything is built on top of that. And all of a sudden the RBFs work a lot better because they're going to 0 when you get off the other side there. Of course, all this stuff is done simultaneously, right? So you don't do one and then the other. You solve the entire thing all at once. And you can do that because you have the power of the pseudo-inverse behind you. There's another parameter here that's also the smoothing parameter. Play with that if you want. Don't if you don't want. It's just a way of shifting and saying, I will sacrifice the need to go through each one of these data points in favor of making a smoother curve. So if you have data that looks like this, obviously you don't want your surface to be quite so bumpy like that. You want something that's nice and smooth. That's what the smoothing parameter in here and in the documentation you're going to see it's called lambda. Okay, sample Gaussian. This is in 1D. We're going to use the SciPy interpolate RBF interpolator to find the answer to this. Documentation, frankly, Gemini will spit this up too. Sometimes I find Gemini, by the way, resorts to older versions because it's been trained on the older versions. It's not actually up to date on the modern versions. Just in case you're using that and it's like, okay, well, this isn't working. Wonder why not? That's what's happened. I think since it got up to Gemini 2.5, then that's a lot better because it's like kind of dynamically scanning it in the background, but just put that out there. Right? So we've got our true function. Here's this nice W. Data point sampled there, and the RBF interpolator does a pretty good job. Can't argue with that one. The 2D one, again, isn't working, obviously. Run all. Run anyway. Right? Not surprisingly, it's going to look, well, basically the same as the other one because it's still tied into to 0 here. All right. Anyway, there you go. Right? So that's our original curve, and that's the RBF version of it. And I can't go back to the previous tab thanks to the search thing. Okay. What have I got left? 9 minutes. Okay. That's it for curve fit. Any questions? Curve fit, interpolation, pseudo-inverse, weights.